Okay, welcome to EGR445. Couple of announcements. We are on our final stretch. We are going to discuss internal combustion engine. We are going to discuss the internal combustion engine design, and we will wrap it up with flywheel testing and flywheel design and testing. So this Thursday, there won't be a class, but instead we would be meeting in the simulator building. In the simulator building, there is this glass engine that we will be studying, and we will perform some experiments on the glass engine. If time permits, I will give you a tour of sim building where there are engine cutouts, different parts of the engine, and also I will take you to the automotive shop and actually show you what are the physical systems that are used to build the engines, what are the different subcomponents, and so on. So this Thursday, we will directly meet at simulator building at 4:15. If you are after 4:30, unfortunately, the gentleman who is going, the lab manager there, is very strict about timing. You may not be allowed to enter the lab. So please be there at about 4:15 to 4:20. Simulator building. So that is one important point. If you look at the email, first floor lobby. Okay. So I would be there. So you can just wait outside. I'll come and we'll go in the lab. Another important thing, you should be wearing closed-toe shoes and bring safety glasses, because dealing with engines is dangerous. So please bring safety glasses and wear closed-toe shoes. And what we are going to do is, first, we'll discuss about the engine. I will talk about the various parts of the engine. Then we will run the engine. We will see how the flame front propagates. What do we mean by spark advance? How do we mean by spark retard? How the valve timing diagrams get changed. Then we are going to do something called as the dyno test, wherein we would load the engine and see how the engine performs, what are the torques and powers that would come out of engine at different speeds. So it's going to be a lot of fun. It's going to be loud. So in case if you want to bring some earplugs, that would be fine as well, because we would be working with engines. Safety glasses are required. You will also see actual combustion happening inside the engine. And we will also connect, there is an eddy current dyno, which is sort of the load on the engine. We would vary the load, we would see the performance, we'll measure the fuel consumption, and so on. So this Thursday, we will meet at simulator building. But there is one exercise that I would want you to do before you come. And that exercise is completion of tutorial 1 for Lotus simulation software. And has anyone done it? Don't worry, just for you, I have finished the tutorial and uploaded the solution onto Canvas. So what you should do is, you should download the solution and try to run it. And I'm going to share my screen. That way I will show you what needs to happen. So you have to open, first you have to go to Canvas, and on Canvas there is a .sim file that you need to download. That sim file contains all the components that you need to run the simulation. So run open Lotus engine simulation, open an existing .sim file, click OK, and then what you do is you can import that .sim file into Lotus engine simulator. This is schematically how the engine looks. So what is it? So what you have is, you have intake, you got intake information, you got fuel information, you got fuel, so you can actually choose port injection, gasoline, you can do the calorific value. Then this is the intake element that you need to apply, that indicates the piping and the stuff. Then you have the valve, and please understand, depending upon the type of valve that you use, you can actually choose the appropriate lift profile for valve. How does valve open? How does valve close? Then what you have is, you have something called as cylinder, and cylinder has all the important dimensions. Like the important part is, let me just attach this over here. Important part is bore diameter, which is the diameter of the cylinder, stroke length. Then you would also have the compression ratio. 9.5 is a typical compression ratio for gasoline engines. Then you can actually add clearance, other things can get calculated. Depending upon the type of combustion that you are going to expect, you can model different combustion models. You can actually do surface temperature, scavenging efficiency, all that stuff. So this is where the piston and cylinder information gets put in. Then you have this exhaust valve, and you can change the valve parameters, you can change the lift properties, you can do all the stuff. You got the exhaust manifold or the exhaust port, and you got the exhaust duct or the exhaust element. If you want, you can add a muffler to this, and you will see how the performance of engine would change depending upon the muffler. Because what does a muffler do? Muffler reduces the exhaust noise. Essentially, it muffles, but it adds a back pressure. So it creates an obstruction to the flow. That obstruction to the flow results into reduction of power. There is turbocharger as well, so you can make the engine turbocharge and see how the performance changes. So here is something that I want to tell you. Here, this is the basic model. The engine that we are going to run, it does not run on pure gasoline. It's a special mixture, because gasoline engine, gasoline will not burn efficiently in a glass engine and a graphite piston type of assembly. So what we would do is, we will actually see what type of fuel is used. Then you can have to go to this, change that particular fuel, whether it is some sort of kerosene, combination of kerosene. Then depending upon whether the fuel is carbureted, whether the fuel is port injection or direct injection, that I think it's the fuel there is carbureted. So we'll change these parameters. And then what we would do is, we'll try to approximate the valve dimensions, and then we will change the dimensions of piston and cylinder assembly. After this is done, what I want you to do is, I want you to go to tools and do data check wizard. This is the first thing that you will do before running the simulation. Go to tools, data check wizard. Data check wizard will actually go through all these elements and see if everything is okay. The links are okay, the cylinders are matching with the ports, and all that type of information that needs to be there. It requires what type of test are we going to do? Are we going to do a transient test, or are we going to do a steady state test, or are we going to do some type of a road cycle? So that information gets from here. So if you go, let me see. So here, can you see that this is for the steady state vehicle simulation? So here, what is going to happen is, you are going to run the engine or rev the engine from different RPMs, 1000, 2000, 3000, 4000, 5000, 6000. Gasoline engines do red line after 6000. So you generally don't go beyond 6000. So we are going to rev the engine in these ranges, and then these will be the test points and the simulation will be carried out. And then you can actually change depending upon what type of engine you have, what type of fuel efficiencies you have, what type of boundary conditions you have, what type of friction you have, all that stuff you can do. But once this is done, you are ready to run the simulation. And then what you do is you click run. When you run, it's going to ask you for the label. And I'm going to say test 1. I would say test 1. I would say test 1. And then what I would do is I would run. And since this is a very simple simulation, this will run in a flash. If you have a very complicated system with different valve openings, closing, different valve profiles, maybe some complicated friction model or complicated combustion model, it will take time. But now once you click launch, it will tell you about the errors. There are no errors. There are just warnings. So you can ignore these warnings. Now it will run through the simulation. The solver would run and you will get the solution. And it will tell you what do you want to see. So you can see the load test conditions. You can do the graphical results and then you can say load. And once this is done, you can go to result. And in the result, you can see result viewer. This result will tell you all simulation information, like what were the coefficients, what were the valves, what was the, so something that I want you to understand, which I would discuss in detail as we go through the theory, is this gives you the cylinder, bore, connecting rod length, then it will give you the valve closing and opening diagrams. So for valve number 1, you are opening 10 degrees before top dead center. You are closing 66 degrees after bottom dead center. The dwell, which is the valve, when the valve profile is flat, the dwell is 0 degrees. Maximum lift of the valve is 8.5 millimeter. And this lift diagram is polynomial. And then you got exhaust valve, and that is what it says when exhaust valve opens and exhaust valve closes. So this information is useful for opening and closing the valve. So this is something called as valve timing diagram. And in IV Tech engines like Honda, these valve timing diagrams, they are dependent on speed, so they get changed. And then you can actually go through all this information, and then it will actually tell you the load test profiles, and then all this information from the solver is plotted graphically in, let me show you, go to results, results graph. So what you have here is you have torque versus speed. Can you see the torque in Newton meters? That is blue, and engine speed. So as engine speed changes, how does torque change? As engine speed changes, what is the power output of the engine? So as you can see, that red line is the power output. As speed is increasing, the power is increasing. Torque line is fairly flat. Then what is called something called as brake specific fuel consumption. So what is the amount of fuel consumption per kilowatt of power at the tire? Brake specific fuel consumption is given as grams per kilowatt hour. How much fuel that engine would consume in 1 hour to generate 1 kilowatt. That is called brake specific fuel consumption. Then on the right hand side, that is another important parameter that is used for design, which is BMEP. BMEP is called as brake mean effective pressure. So as the suction, compression, expansion, exhaust strokes are completed, the pressure inside the cylinder fluctuates. So brake mean effective pressure is the average pressure inside the cylinder for the entire duration of cycle for that particular cycle, and that is given in bars. So brake, so these are important engine parameters. So here is what we want to do. When we go there, I want you to have this simulation on your laptops. We will go look at the engine, then we will find out the bore, stroke, valve information, fuel properties. We'll plug all that information in this model, run the simulation. We will have these plots, and then we will do the actual experiment and see how good our results look like. Our results are not exactly on spot on, but they would be similar. So you will see the trend, and you will see that the theoretical calculations, they would give you some good, reasonable approximations of practical testing results. So this is what's going to happen on Thursday. Please understand, this exercise is purely voluntary. So if you don't do it, you don't have, if you don't want to do it, you don't have to do it. But I would strongly recommend you do it, because this will add to your knowledge. So any questions from my online students before I stop sharing this Lotus engine simulation screen? Does anyone want me to run through this process again, or everyone is comfortable with how? Yeah, of course. If you want to do multi-cylinder engines, go to help. Actually, don't go to help. There is a tutorial that I have uploaded on that. In the last class, I kind of discussed different tutorials. You can do multi-cylinder engines, you can do super complicated engines, and this wizard would do it. And I use this wizard to actually on a practical Honda engine, on a diesel Gunt engine, and this works very well. So any questions from my online students? Any questions? Yeah, there is a question. No questions. Okay. So somebody made a no. So with that, I'm going to stop here, and then we will start with the design of internal combustion engines. So let me ask you, are there any questions related to the content that was discussed in last class? So in last class, we talked about different types of engine. We talked about different components of engine. And today I want to talk about a little bit in detail about different strokes, like 4-stroke engine and 2-stroke engine. So please understand, suction, compression, expansion, and exhaust are the 4 strokes. In 2-stroke engine, 2 of these strokes are combined together. So for an example, if you have a weed whacker engine is a 2-stroke engine. In 2-stroke engine could be a gasoline engine or could be a diesel engine. How would you know if an engine is a 2-stroke or a 4-stroke? So no.
They don't have valves or
correct. 4-stroke engines would have valves. And 2-stroke engines have ports. So that's why the two-stroke engines are easier to construct, cheaper to manufacture, and inexpensive, and they last a lot. Unfortunately, efficiency of four-stroke engine is greater than efficiency of two-stroke engine. Pollution of four-stroke engine is lower compared to the pollution of two-stroke engine. Four-stroke engine torque is lower compared to same size two-stroke engine. Then four-stroke engines, usually what you have is you have an oil sump, and that is where the lubrication reservoir is. So every time the engine, there is an oil sump. So oil sump or pan. In two-stroke engine, the oil is mixed with the fuel. Oil mixed with fuel. So if you see a weed whacker engine, which is a two-stroke engine, you will see that white smoke coming out of that engine. That is the unburned oil and hydrocarbons that are coming from that engine. Four-stroke engines typically burn cleanly. So power to weight ratio for the four-stroke engine is low. Power to weight ratio for two-stroke engine is high. And the other thing in the case of two-stroke engines are used when you want a compact engine that is delivering more power, and four-stroke engine is you want a more fuel efficient engine. So for an example, the boxer engines that are used in some motorcycles, they are two-stroke engine because they are designed for reliability, for lasting a long time, and more power output. So what happens in four-stroke engine? You have suction, compression, expansion, exhaust. So 0 to 180 degrees, suction takes place. 180 degrees to 360 degrees, compression takes place. 360 to 540, expansions takes place, and from 540 to 720, exhaust takes place. Now, what does that mean? So, say in terms of valves, you have an intake valve and you have an exhaust valve. So please understand, this is 0, this is 180, 0, 180. So here is what's going to happen. From 0 to 180, the exhaust valve is going to open. Inlet valve is going to open. Exhaust valve will be closed. This is cycle 1, so A. For cycle B, which is compression, intake valve will be closed, exhaust valve would be closed. For the expansion, intake valve would be closed, exhaust valve would be closed. For exhaust, the intake valve will be closed, but the exhaust valve would open. So this is C, this is D. Now, if you understand the valve timing diagrams, intake valve does not open. So this is TDC, this is BDC. Intake valve typically opens before TDC because air needs some time to go in, and closes after BDC. and exhaust valve opens before TDC. If you look at the exhaust valve, it opens before TDC and closes after BDC. This overlap is needed because air has some inertia, so that air needs to go out. But here, so please understand what it means is there is a duration of time when the intake valve and exhaust valve, both of them are open. We need to minimize that, because that means a fresh charge could enter from inlet and escape from exhaust. So we need to make sure that overlap is minimized. Many a times what they do is they design the ports in such a way that the intake charge actually pushes the exhaust charge out. So when you look at the shapes of the combustion chambers, shapes of the cylinder heads, those shapes are not flat. There is a particular aerodynamic shape given to the intake side and onto the exhaust side on the cylinder head, because you want the intake fresh charge to expel the exhausted charge to the exhaust port, and then that fresh charge should be compressed and then burnt. In the case of two-stroke engine, what happens is you do not have valves, you have ports. So what the way it works typically in two-stroke engine, you have something called as a transfer port, and the engine is something like this. And so think about it something like, I want you to be comfortable with how this is. This is where the intake charge is coming. This is where the exhaust charge is going. So what you have is you have the fresh incoming charge that comes here. Throughout the rotation, this intake charge is compressed, and then it actually goes from this transfer case onto the front and gets continuously compressed. When this piston goes to the top dead center, you get a spark. So there is a spark plug, you get a spark, and basically this spark plug propagates the flame front, and you have the expansion stroke. So what is happening is as one stroke is happening above the piston, the other stroke is happening below the piston, which means these two strokes get combined, these two strokes get combined. That's why in 0 to 180 degrees, you have two strokes happening, and 180 to 360 degrees, other strokes happening. So 4-stroke require 2 revolutions of crankshaft to finish the entire cycle. 2-stroke will need only 1 revolution of the crankshaft to complete the cycle. That's why it is called as 2 strokes, and that's why it's called as 4-stroke. In the 2-stroke engine, usually on the intake side, the oil is sprayed into the charge. And that's why if you see those feedbacker engines, you don't have a separate oil cylinder or separate oil sump. You mix the fuel and oil together and then basically run those engines, because the oil is pre-mixed. In the case of 4-stroke engine, just like your cars, the engine is in the oil pan, and you have to periodically go and change the oil. So that's what you do after every 3,000 miles, you get the oil change. So these are the most important things between 4-stroke and 2-stroke. So please understand, as a mechanical engineer, you would be expected to know the difference between gas engine and diesel engine. You would be expected to know the difference between 2-stroke engine and 4-stroke engine. But then nowadays, what you can do is you can actually modify these and get to hybrid engines. And we have a course that talks about electric hybrid engines. So there's a course in automotive concentration that you are welcome to take that will talk everything about electrification and automotive engines and hybrid power plants. Okay. Now, what we are going to do is we are going to go and start the design or design principles of the single cylinder engine. Any questions, conceptual questions on how engines work? What are the different approaches for engine design? So one thing I want you to understand, in my past, about 8 or 10 years ago, as you can see, this connecting rod and this crank, they have an articulation. So they have a hinge joint. What we did, we converted this into a gear assembly and made this like a straight joint. So there was no articulation that made the engine super compact. That is called as the hypocycloid engine. So if you Google, we wrote a couple of papers on design of Weissman hypocycloid engine, where the connecting rod and crankshaft, they are made up with one solid piece. Any questions from my online students about the engine design? So how does an engine, a single cylinder engine, looks like? A single cylinder engine looks something like this. It has a piston. This piston is flushed with the cylinder. So this is cylinder. This piston has grooves. And through these grooves, there are rings. These are called piston rings. There could be one or two. At the end, there is something called as the oil ring. The purpose of the oil ring is basically to scrape the oil off of cylinder wall. And then here, there is something called as the piston pin, also called as the gudgeon pin. And on one side of the piston pin, you have the small end of the crankshaft. So there is a small end. On the other side, there is this large end, the crankshaft. And then this large end of the crankshaft is fitted onto the crank. And please understand, this whole thing is going to be super duper hot. So for that, there will be either you can add a cylinder liner. So sometimes you have a cylinder liner, or you can just have the regular cylinder, and then there will be a water jacket. So this would be the oil that would run through the cylinder block, and finally that would be cooled in the radiator. Then there will be the cylinder body. So this is how the body would look like. And what I'm showing you here is the stationary cylinder. This is not an automotive engine, but this is just to indicate, or this is just to show you how the typical cylinder, piston cylinder assembly looks like. So you have something like this. And then usually what you have is, here you have some type of a scooping mechanism. Here there is this oil. And the bottom end of the crank continuously runs in oil. And every time that cranks run to the oil, this oil gets splashed on these surfaces. Sometimes in the automotive engines, what you have is you have an oil pump. What does that pump do? That pump will actually, through the cylinder bores or through the jackets, it will actually lubricate all the parts of the piston and cylinder. On top, there is going to be a cylinder head. There will be cylinder head. This cylinder head would have a gasket for sealing. Remember, does anyone have head gasket failure on their cars? That is very expensive to fix. You have a cylinder head and there is this gasket, and then on top you're going to have the cylinder dome, and usually here you have the intake and exhaust ports, and then you have valves, and then here you are going to have your spark plug. So I haven't shown you the valves. This is intake valve, this is exhaust valve, this is the spark plug. This is the piston. This is the cylinder. This is the cylinder liner. This is the cylinder. This is the water jacket. This is the connecting rod, also called as con rod. This is the crank. This is the oil sump. This is the head. This is the gasket. This is called as the crank pin. This is called as the piston pin. And how does piston look like? So I'm going to show you the piston would look something like this. Usually piston is made up with aluminum, and the reason it's made up, sometimes it's made up with cast iron too, because there is a lot of heat, and it will look something like this. This is where the piston pin goes. And there is circlip on both sides so that the piston pin can be retained. This is where the connecting rod fits on the piston. There are grooves. This is the combustion chamber. These are the grooves for the ring. So basically you have something called as the piston ring, and then you have a scraper ring or oil ring. Scraper ring, oil ring. Yeah. So that is how a piston cylinder assembly looks like. Gasoline engines are spark ignition. Gas engines are spark ignition, and diesel engines are compression ignition. So the difference in the diesel engine is there won't be a spark plug, but there will be a fuel injector. So please try to understand, in the case of, so gas engine is a homogeneous mixture. air fuel mixture. So what do I mean by that? Which means you have the fuel, you have the air, fuel is sprayed into the air or carbureted into the air, and that air fuel mixture is fed through the intake valve. So it's sort of mixed. In the case of diesel engine, only air is compressed and goes through the intake valve. And what happens is at the end of the compression stroke, the air, the pressure and temperature of the air is so high as that small mist of diesel is injected onto the air, that fuel spontaneously burns. So for that, you need to have certain air fuel ratio that is called as stoichiometric ratio. If you have too much air and too little fuel, the fuel is not going to burn. If you have too much fuel and too little air, the fuel is not going to burn. So there is a particular range. You should have certain amount of fuel and certain amount of air. Only then the fuel will burn efficiently. If the fuel does not burn efficiently, then basically you see cars smoking or cars knocking, or you would have some type of pinging sound from the engine and so on. Now, one thing that is important is we want the combustion to start at a particular location. We do not want spontaneous combustions inside the cylinder, because that will result into flame fronts colliding with each other. Let me repeat once again. So you have this cylinder. What you want is, you want your spark over here and you want your flame front to propagate like this. But many a times what happens is, you can have the combustion starting from here, and what that will do is, these two flame fronts will collide with each other, and that will actually drop the engine efficiency down, and it will start engine misfiring, or it will start engine knocking. So what they have is, they have something called as octane level. So 87, 91, 93, that basically tells you about the amount of additive is in the fuel that has anti-knock properties. So what usually happens is, when the car starts knocking, you retard the spark. You let some more time for the combustion to take place. Then second thing is, many a times what you have is, you have EGR, exhaust gas recirculation. Because please understand, we need to have this combustion under critical control. If the temperature of piston is too high, then the piston would slap. If the temperature of cylinder is too high, the cylinder would expand and the gases would leak, and that we don't want. We want it to be a super controlled combustion. So the way we control the combustion is by advancing and retarding the spark, and then we are actually changing the air fuel ratio. That depends upon the O2 signal, oxygen sensor that you get before and after the engine. Then we also have something called as the NOx sensor. NOx sensor is nothing but a teeny tiny microphone that is detecting sort of the noise. And based on all that information that gets fed to the ECU is controlling these engine parameters so that the engine is running at the desired efficiency. So believe it or not, engine design is a very, very fascinating subject. So one can spend his or her own entire lifetime just studying engines and making different types of engines and making them more efficient. Any questions? So what are the main parts of the engine that we are going to study? Can someone point out the main parts of the engine? Piston, cylinder. So we'll first look at the design of cylinder. Then we will look at the design of piston. Then we will look at the design of connecting rod. Then we would look at the design of crankshaft. And then I will look at the design of flywheel. And by the way, the design slides for all these are already uploaded. Now, then we will look at design of valves, puppet valves. Then if you want, we can look at design of camshaft and so on. These are the main components of engine. One thing before I start discussing, I just want to spend some time on this flywheel. Flywheel is like a capacitor. Now, please understand whether the engine is 2-stroke or whether the engine is 4-stroke. Out of those suction, compression, expansion, and exhaust, only the expansion stroke is where the power is coming out of engine. Let me repeat. Suction is going to consume some power. Compression is going to consume a lot of power. Exhaust is going to consume some power. The only part where the fuel is burnt is in the expansion stroke. So if you look at the torque versus crank rotation, so this is 0 degrees, 180 degrees, 270 degrees, 360 degrees, and so on. Actually, let me just make it simple like this. So this is suction is going to take power. So if you look at suction is going to take power, compression is going to take power, only the power is going to be expansion, and then exhaust is going to take power. So what you have is, as you go through this system, as you go through this power cycle, this is the negative work, negative work, negative work, and this is where the power is coming out. The chemical energy in the fuel gets converted to mechanical work. So unfortunately, if we continue to engine run like this, what that means is there would be a power spike during one cycle, and then there will be significant drop during other cycles. So what we do is, to the side of the engine, so this is the engine, and I'm going to show you a stationary engine. What you have is, you have a big inertia wheel. This is called as the flywheel. So what happens with this flywheel? Flywheel is like a capacitor. It stores energy during the expansion stroke, and the flywheel powers the suction, compression, and exhaust stroke. So even though you don't notice it, the flywheel speed gets changed in every stroke. So basically, flywheel is storing energy, this huge energy, and it's giving out part of the energy during suction, compression, and exhaust stroke. So that is the function of the flywheel. So we will talk about flywheel design towards the end of the class. But today, what I want to do is, I want to discuss cylinder design. So design of cylinder. So cylinder design, if you look at it, if I take the cross-section area of cylinder, it's going to look something like this. So the first one is longitudinal stress. That is sigma T. is given as P times D divided by 2T, where D is the diameter of the cylinder, P is the pressure inside, and T is the thickness. Now, I just want to be clear about the energy flow here. So think about it. First, you have chemical energy. This chemical energy gets converted to mechanical energy. This mechanical energy, there is some friction, and this is available at the brakes or tires. So what you have is, you have, say, this big amount of reservoir of energy. Not that entire energy can be converted to mechanical energy, because what you are trying to do is, you are trying to convert a low grade energy, which is heat, to a higher grade energy, which is mechanical work. So you are going to have significant amount of losses. On the other hand, if you look at the electric vehicles, electrical energy is the same level of mechanical energy. That's why electrical motors are more efficient than the internal combustion engines, because it's difficult to convert the heat energy. Chemical energy gets converted to heat energy gets converted to mechanical energy. So basically you are going upward slope. So you are going from low grade energy to high grade energy. That's why efficiency of internal combustion engines is somewhere between 25 to 35%. Now, once you have the mechanical energy, what you have is, you have frictional losses. You have the losses between the piston and cylinder. You have losses in the valve train. You have the losses in the crankshaft. Every rotating component is going to consume some amount of power. So what you have is the power that is inside the cylinder. So let me talk about this. The power that is generated inside the cylinder is called as indicated power. And the power that is available at tires, tire or brake, is called as the brake power. Now, which power do we care about? From usage point of view, I don't care the amount of power that is generated inside the cylinder. I'm focusing on the amount of brake power that is available to me, because that is the power that can be used to do the work. But indicated power is the power that needs to be generated inside the piston cylinder assembly. So what it means, that when I design the cylinder and when I design the piston, it should be designed in such a way that it can sustain the pressures and temperatures that are required to develop indicated power. So what you have, this pressure is the pressure inside the cylinder. So this is actually indicated pressure. So, and if you look at the PV diagram, if you were to plot the PV diagram would show you the indicated pressure. So you can have mean effective indicated pressure, and the pressure that is computed from the brake power is called as the brake pressure. So this gives you indicated pressure. From here, it gives you brake pressure. So when we design, this is the classic formula for the thin shells or thin pressure vessels design. So you have the longitudinal stress, PD by 2T, where P is the indicated pressure, D is the diameter of the cylinder, and T is the thickness of the cylinder. This is the stress across the longitudinal axis. And there is a stress around the circumferential axis or circumferential stress, which is called as the hoop stress, which is sigma C is equal to P times D divided by 4 times T. Do you do pressure vessel designs in design? Did anyone do pressure vessel design? Design of thin pressure vessels, thick pressure vessels? No? Okay, so this basically is considered as, let me ask you a very simple example. If you have an soda can, aluminum can, okay, and by mistake, you put that in freezer. By mistake, you put that in freezer. Where does the can crack? Correct. And that is the reason why the aluminum can, soda can, cracks vertically, because the longitudinal stress, if you look at both these equations, sigma L and sigma C, circumferential stress, pressure is the same, diameter is the same, but the longitudinal stress is significantly higher. That kind of sort of shears or cracks the shell, and that is how the soda can feeds. Everyone understood, my online students? Yes, so what I'm trying to say here is, if you have this soda can, okay, maybe Diet Coke, and if you put this in the freezer, you would see that it cracks like this. Very rarely you would see it cracking. Some. Now the problem here is the way it is manufactured. This basically is crimped on top. So I don't know if you know how these soda cans are manufactured. They are actually, there is something called as press tool design. Press tool design means how do you take the sheet of metal, design the punch and die, so that when the punch hits the die, basically you draw the shape that you want. So basically what happens is, if you look at the soda can, from top to the bottom, it's just one piece. But if you look at the lid is actually put on it. So basically it is actually crimped. And sometimes, I don't know, depending upon the pressures that you use, it could be fused. So pressure tool designs usually, there are two ways to look at this. If the thickness is much less than the diameter, it is called as the thin pressure vessel, and these equations are correct. So if the thickness of the shell is significantly lower than the diameter, then it's a thin pressure vessel. Sometimes the thickness is quite large, so then it is considered as a thick pressure vessels. So the boilers or the turbine plants, the pressure vessels that are used are not thin pressure vessels, but they are thick pressure vessels. But for internal combustion engine design, typically we use the thin pressure vessel design. Okay, so what are the steps? Whenever you are going to design an internal combustion engine, you want to find out what is the maximum pressure inside the cylinder. It could be either the design parameter, or that could be given as part of the brake, in the brake power that you need. You have DO, which is the outside diameter. You have DI, or just D, which is the inside diameter. And you have T, which is the thickness. And you have something called as 1 over m, which is the Poisson's ratio, 0.25. So what you do is you calculate something called as apparent longitudinal stress. And that is pi by 4 b square p, which is the force on the piston. So if this is the diameter, you know the maximum pressure, so you know the maximum force, so this is the force. Divide that by the area. So, and this equation, you will also calculate apparent circumferential stress, which is D times L times P divided by 2 times T times L, where L is the length of cylinder. And from these two equations, you can find out T as P times PD divided by 2 times sigma C plus some allowance for reboring. So what is this reboring? So usually what happens on the stationary engines, after the engines runs for 100,000, 200,000 miles, clearly they don't run miles. So after some time, the cylinder basically gets worn out. So what happens is you basically take the piston out, you bore the cylinder, put a new liner inside, and then that cylinder is as good as new. So that's why what we do is we basically gives a little bit more thickness so that we can actually machine the cylinder later. Then sigma C values is equal to 35 typically Newton per millimeter square to all the way to 100 Newton per millimeter square. So now again, what are the different values of C? So for that, you need to refer to the table 32.1, wherein they give you the value of diameter and they will give you the value of allowance. So for an example, if the diameter is 75, you're going to have 1.5 millimeter. If the diameter is 100, you're going to have about 2.4 millimeter, and so on. So next part is, let me give you what I just said. There is BP, that stands for brake power. This is power available at brake. IP is called indicated power. This is power developed by engine. So please understand, IP is always greater than brake power. IP minus BP is nothing but mechanical losses. So what you have is something called as, you have efficiency indicated. indicated efficiency is the ratio of brake power divided by indicated power. Now, what is power? Power, I'll start with a very basic definition. Power is work divided by time. What is work? Work is force multiplied by distance. In the cylinder, the force is generated by pi by 4 d square multiplied by pressure, and the distance that is traveling is nothing but L, which is stroke length divided by time. So now what I'm going to do is I'm going to combine these terms together. So what I have here is pressure multiplied by volume per time. So please understand, cylinder volume is not going to change. Why is it not going to change? Because the diameter is going to remain the same. The stroke length is going to remain the same. But depending upon what power you are looking at, pressures are going to be different. So let me ask you this question. If brake pressure, it's also called as brake effective pressure or brake mean effective pressure, and then you have indicated mean effective pressure. So efficiency indicated is also the ratio of brake mean effective pressure divided by indicated mean effective pressure. Now, one thing I want you to understand. Remember when we ran Lotus engine simulation software, we found out it gave us the plot between the brake mean effective pressure versus speed. Do you agree with me? Because brake power is something we can readily measure. We can put the engine on the dyno and we can measure the power and we can find out brake mean effective pressure. But for the piston and cylinder design, what we are really interested in, we are interested in the indicated mean effective pressure. So using the efficiency equation, once we know the brake mean effective pressure, we can find indicated mean effective pressure. Similarly, you can find out the fuel consumption. If you find out the fuel consumption per unit of brake power, that is called as brake specific fuel consumption. So fuel consumption divided by brake power. This is brake specific fuel consumption. And there is ISFC, which is indicated specific fuel consumption, that is based on fuel consumption divided by indicated power. So again, okay, let me see. Can I finish this? Okay, I think I can finish this. So indicated power, I just gave you the equation PM L times A times N by 60, where N is the RPM for two-stroke engines. And please understand, for four-stroke engine, you take 2 revolutions. So indicated power is PM L A N by 2 divided by 60, which is for four-stroke engine. So L is a stroke, A is the bore area and N is P. Bore to stroke ratio, which is basically also called as the famous L/D ratio. So if you have a square engine, the diameter of the cylinder and the stroke of the engine is same. This is usually anywhere between 1 to 1.5. And the next part is design of cylinder head. Which is you have designed. So what is important in cylinder design? Bore, stroke, the thickness. Now, once you have designed your cylinder, you have to look at what goes on the top. And usually you have a cylinder head, and the cylinder head is bolted onto the cylinder. So the thickness of the cylinder head is diameter multiplied by C times P divided by sigma C. That comes from the circumferential stress, where D is equal to dia, P is equal to max pressure, sigma C is allowable circumferential shear stress, 30 to 50 Newton per millimeter square, and C is a constant, typically 0.1. And the last part is what you do is you determine the bolt sizes. So depending upon the forces, so force here is going to be pressure multiplied by area. You would divide that by the number of bolts is equal to sigma T multiplied by the area of bolt. And that would give you the bolt design. So this is pretty much the cylinder design. Next class, we are gonna do some experiment. And then after we come back, I would work out a problem. So with this, we are gonna stop here, and then I will see you on Thursday.